Hello, my name is Bryan, and I'm going to tell us about the topic of relative stability for the subject computerized control. Well, as we know, there are two types of stability. The first one is absolute stability and relative stability. But in this case, we are going to talk only about relative stability. But in general terms, the absolute stability tells us if the system is stable or is unstable. Well, relative stability tells us that once it is established that the system is stable, it is defined how stable the system is. We can see that it is a degree of stability. Another definition is that it's a quantitative measure of the speed with which the response of the system tends to stabilize, or in other words, go to zero. Relative stability is divided in two types, or in two orders. The first one is the limitedly stable first order. This order tells us that a system is limitedly stable if there is only one pole at the region, as we can see in the picture. And the others being in the negative plane. Also, it tells us that when it has a pole at the zero and we apply an impulse to it, right here, an impulse right here, the system will remain stable as if it were a step, but we don't know if later it remains stable or no. So we do an impulse and we can see that it's stable, but we don't know that it later will remain stable or no. And we have the second order. This means that a marginally stable system has poles on the imaginary axis and none in the right plane, right here in the imaginary axis. And what it means to us is that the system is going to oscillate under the limits of the poles, right here. There are the limits, upper and over. And the average is zero. So our system is going to oscillate between the poles. And to measure how stable is our system, we have the Nyquist criterion. And it says that when we design a control system, it is necessary that it be stable and have adequate relative stability. The Nyquist traces indicate whether a system is stable and the degree of stability of a stable system. So the Nyquist stability criterion relates the open loop frequency response to the closed loop stability and is based on a complex variable theorem that is based on the mapping of the contours in the complex plane. And for the Nyquist criterion, for a TS that encloses C zeros and P poles of the EF function without passing over any zeros or poles of EF. The EFS will enclose the origin clockwise a number of times equal to n equal C minus P. And here we have a block diagram of the function. We have that Fs equal 1 plus Gs times Hs. We have that C is the number of closed loop zeros of the function in the right half plane of the plane S. And P is the number of poles of Gs times Hs in the right half plane of the plane S. And finally, we have that the N is equal to C minus P, that is the number of clockwise turns that makes the function to the origin. And this is the simulation in MATLAB. Here we have a function that is stable, and that is stable, and here is the MATLAB simulation.